of the two components doing work? Fgx or Fgy? Fgx. So if I am able to find between Fgx and the displacement delta x, right? If I am able to find the angle between Fgx and delta x, will be easier to work with. Unless that you remember that it's this angle, so the angle between the two forces, which is easy to find, is the complementary angle. But if I go by the gravity, what is the force doing work? Mgx, I will use mgx times the velocity times cosine of the angle alpha between mgx and the velocity. Mgx is going up or down? Down. If down is my positive direction, down is my positive direction, will be, what is the angle between mgx and v? 0 degree. So what is alpha in this case? 0 degree, right? So, and what is mgx? And what is mgx? mg sine theta. mg sine theta times the speed, right? And the mgx in this case, because it's going down in the same direction than this, the rate of doing work will be positive. When it's going up, the rate of doing work will be positive or negative? Negative. This is one way. The other thing is to get mg v and cosine of the angle between mg and v. This angle is 60 degrees. Sorry, let's say 30 degrees. Or theta. And this angle is 90 minus theta. 90 minus theta. Everybody can see that? So if we have this, you can see here that if I have this and the gravity is in this direction, this angle, which is this angle between the displacement and the velocity, is, if this is 30, this is 60, which is 90 minus theta. And cosine of 90 minus theta by the identity, cosine of 90 minus theta is the same than sine of theta. This is an identity, math identity. But you need to remember that. For this reason I said that it's better to say, okay, mgx, b, cosine of the angle between mgx and b. And it's easier to work with, you know, than to remember this identity. Otherwise, if you have numbers, you plug it in. 90 minus theta is very easy, but you need to remember that that angle is the one needed, 90 minus theta. All right, those are the questions, the type of question with power. When we have power, they will ask, find the rate of doing work. You need to get the force, you need to get the velocity, and you need to get the angle between the force and the velocity. And you just use force, velocity, cosine of the angle. You find it, and that's the rate of doing work. Any questions with power? We finished with energy. I covered the two study guides, the different theorems. So as you can see, energy has a lot of theory, but it's not a very difficult topic. No, I give the force, find the work. I give a graph of F versus R or versus X. How do you find the work? A graph. The area under the curve. If the area is above, positive. If the area is below, negative. Good. This is the typical problems when I give the force, different forces, and you get the work by each force. If you add it, you get the net work. If you get the net work, you can get the change in kinetic energy. If you have the change in kinetic energy, or you have the kinetic energy initial or the velocity initial, you can get the velocity final. You use the first theorem when the forces are given explicitly. Second theorem, when the forces are not given explicitly and there is no non-conservative force. Third theorem, when there is no non-conservative force and we work by inspection. This is if I give the potential, the force as a function of displacement, you use this equation to find the change in potential energy. If I give the potential energy, you get the derivative, negative the derivative, and you get the force. This is a concept. Good. And finally, the concept of power. In EI is equally final, we use the pendulum. And the pendulum, I gave a specific formula for the pendulum. This is pretty much what is the chapter. Energy is very important chapter because once you understand energy, you understand pretty much to work in physics any problem, and will be very useful in other topics of physics like electricity. So now, if you understand energy, you can solve all the problems that we learned before with Newton's laws. You can do it from energy perspective without doing free body diagram. But it's the same idea. Any question?
So just make sure, so friction is a non-conservative force.
It's a non-conservative force, or any force. My force, if there is friction in the system, my force will be non-conservative. What are the only two conservative forces we learn here? Gravity and spring. But if in this case, if I have this, what other force is acting here? Besides, let's say this is moving like this. What other force is acting here besides gravity? No, no air resistance.
Your force?
No, my force is not there anymore. Look. And yes, what force? Tension. So tension, because the tension depends solely on the mg, tension is also conservative force. But it's like not necessarily conservative force. It's that the tension always is acting perpendicular to the displacement and it's not doing work. So it doesn't matter if the tension is conservative or non-conservative. Simple is that doesn't do work at any time, the tension. But the normal force is neither non-conservative or conservative, doesn't matter because it's not doing work. It's the same than tension. So any force that is acting toward the radius in a centripetal motion doesn't do work. So we don't care. For this reason, we use here EI is equally final. Even that we have tension, we use EI is equally final. Tension could be non-conservative. Could be, but not in this case. Okay? The tension will be conservative if I am pulling an object with the cord, but there is friction. My tension depends on what? On the friction, and the friction is a non-conservative force, so my force has to be non-conservative. So, what are the only two forces conservative we learn here? Gravity and spring. All right, let me just look at the syllable one more moment. All right. Okay, so I will stop here. I finished energy and momentum.